we're going to go ahead and jump into this problem. It says draw the shear and moment diagrams for the beam. And we can see the beam here. It's got 20 kips on either end and this distributed load in the middle. For those of you who were here last week or watched the videos that I uploaded this is actually the same problem. I'm just going to show you guys how to solve it in a different way, in an easier way, I like to think. And so this is just knowing the relationships of this beam and how that reflects on the shear and the moment diagrams. So the first thing that you want to do for any problem like this is to solve for the force reactions, because we've got the roller here and we've got a pin here. You guys should know how to do that by now. It's just equilibrium equations and whatnot. So I'm going to go ahead and just draw in what they are. And so we've got AY acting. It's 80 kips going upward. And then we've got BY going also 80 kips upward, which should make sense because this is a pretty symmetrical beam right here, same forces on either side, so these should be equal. So we'll go through. We've already got the dimensions here, the 15, the 30, and the 15. So now we just need to know about how our relationships work. Essentially with these beams, if we're taking a look at shear is always going to change based on how the forces are acting down on that shear. We showed you how they do change by making the formulas last week, so you can kind of get a basis for that idea. But right now we're just going to look at how they do it the easy way. So first thing that I'm going to do, and that you should probably do, is you've got this beam here. I always suggest drawing the free body diagram of the beam above your diagrams, just so you can help visualize and see exactly straight down where everything's acting. So here, if you look at this beam, we can look at the places where the relationship for the shear should change. So it should change here because there's a change in the forces acting on it. So I'm going to go ahead and draw a straight line down from point A. So there's that line. And then this is going to be all the same during the distributed load. And it's going to change again at B. So I'm going to go ahead and draw another straight line down at B. Now sometimes on the exams these graphs and lines are provided for you. Sometimes they're not, but it's always helpful to go ahead and draw those in. And those should be the three different sections. Now the first thing that we're going to look at is shear. And so we'll go ahead and label it as such. It's V for shear, and the forces are in kips, or the units are in kips. Always write this little label off to the side, or when you write in your numbers, write kips with it. But this label and the units are always like a good 1 or 2 points that are just stupidly easy to get. So make sure you do that. So looking at shear, we can look at this. We see the down arrow here with the 20 kips. That should basically show us that the shear goes down 20 kips. So it's just going to be a negative 20 kips right here. So we'll go ahead and write in negative 20. And we look at that, and there's this jump here. Now if we're looking throughout this entire beam here, we should be able to see that there's no other external forces acting on it. And when there's no other external forces acting on it, there's nothing to change the shear. So the shear is going to remain constant in this entire section here. So it'll be a straight line from the left end to A. Hi. Okay, and now we're here at this dotted line where the distributed load starts and there's an upward force at A. So there's two things. We know that the upward force at A will cause it to jump, just like how it caused it to jump down here. And then the distributed load will actually make it go down at an angle. And so we're going to go ahead and draw in the jump first for the force at A. So it's 80 kips. It's going to go up 80 kips from where it is now. So we're starting at negative 20. Going up 80 kips is going to take us to a positive 60. Does anybody have any questions so far about this? Okay. And then now we're here at the positive 60. We need to go and find out where this is going to go from here on out. So one thing we know about this is we know that the slope of this relationship would be the 4 kip per feet going down. So it'd be a slope going downward at 4 kips per feet all the way from A to B. Once we know that, you can multiply out, finding the entire resultant force of this distributed load will end up showing you what the total change is from A to B. So we've got 4 kips, and we can multiply, or 4 kip per feet, my bad. 4 kip per feet, and we can multiply that out by 30 feet. And that should end up giving us a change of, should be negative 4 kips per feet, a change of a negative 120 kips total. And so if we look at that negative 120 kip change, we can go ahead to this line here on the right and go down to where the endpoint would be. So we'd start with the 60 kips over here, and then if we were to take it down the negative 120, we'd end up going down to negative 60 kips. And then from here on out, because this is all acting down and it's the same force acting down the whole way, we can know that it's going to be just a straight line. So we can go ahead and draw the line in like so. And then next thing that we're going to do, we're going to keep going off to the right here. The next force that acts on it that changes the shear is going to be this 80 kip load acting upward at B. So again, we'll find out where we're starting at. We're starting at the negative 60 at B in shear, and the 80 kip is going to make it go all the way up to a positive 20. And then from here on out, from B to the end, there's no vertical forces acting on it, so the shear should not change at all in that little section. So we'll go ahead and have a straight line down. And then lastly, we've got this 20 kip load acting on the end, and it's going to make it jump down. Are there any questions about this shear diagram so far? Okay, I think they're pretty simple, so once you get them, you've got the hang of them. The next thing that we're going to want to do is you're going to want to label where this is equal to 0. And so if we label where this is equal to 0, we'll go ahead and draw a little distance here, and we'll say x, or x1 is equal to. Now there's a couple of ways to figure out this. One way is you could make a cut through the beam here and then solve for shear and then find out when shear is equal to 0. The other thing is you can use a little bit of geometry, which is what I prefer for these triangles here. And it essentially shows us that if we take this 60 and we divide it by our slope, we should get what the x is equal to. It's essentially how slope is rise over run, and we're going to multiply it, we're going to multiply this together, or divide it, my bad, and we're going to end up getting the value down here. So we've got our 60 kips, and we're going to divide it by our slope of 4 kip per feet. And that's going to end up giving us an x1 value of 15 feet. And this is one thing where maybe you could have seen that by inspection, just looking at it. If they're the same force, they go same on the either end, you could guess that the 0 would be in the middle. But it's always a good idea to back up your assumptions with work whenever you can. So we've got the x1 is equal to 15 feet. I'm going to explain that just a little bit more, how I was saying it was slope. So the formula for slope is rise over run. We're essentially dividing the rise divided by rise over run. And the rises are going to end up cutting out just by how fractions work. And since run is on the denominator of the denominator, it's just going to give us run. So hopefully that makes sense to you guys. It tripped me up a little bit when I was taking this class. I wasn't quite sure where the numbers were coming from. But that's how you'll find this distance here for triangular areas. And so we're going to go ahead and go on to our moment diagram. So we'll go ahead and write M for moment. The units are going to be kip feet. So in kip feet, what we need to know is the relationships between the shear diagram here and the moment diagram. Essentially, just how the change in shear was equal to all of the forces acting on it and then the area underneath this, the change in moment is going to be equal to all of the couple moments acting on it and the areas under the shear diagram. Now if we look at this, there are no couple moments acting on it. That means that there's no jumps like we had before. It's all going to be some sort of curve is where your changes in moment are going to be. So we'll go ahead and label these areas as Area 1, Area 2, Area 3, and Area 4. So we've got our areas up here. Now we're going to calculate them off to the side here. So Area 1 is going to be equal to the negative 20 kips that we have there. We're going to multiply it out by 15 feet. And that's going to end up giving us, should be a negative 300 kip feet. And that's ultimately going to be the change in moment from this end to this end. Next, we're going to find our Area 2 is going to be equal to a positive 60 times 15. We divide this by 2 because it's a triangle. We're going to end up getting a positive 450 kip feet. Now, the work for this triangle, it is technically, it's essentially identical to the A2 triangle, but it's just negative. We'll go ahead and write out the work for that. It's going to be a negative 60 times 15 over 2. That's going to be a negative 450 kip feet. And lastly, A4 is going to be equal to a positive 20 in shear times 15 feet. And we're going to get a positive 300 kip foot change in moment. Okay, so now we have the areas. We know what our total changes and everything are. So when we look at this diagram, one thing I'm going to do is I'm going to draw another line from the shear diagram down here to the moment diagram. And I would suggest that when you're working on your diagrams, you do the same. Because this little, where the shear equals 0 is an important part for the moment. So we know that the change in the moment is going to be equal to the area under the shear curve. The next thing we can look at is the slope of the moment. The slope of the moment diagram is also related to the shear, in that whatever sign the shear is at, or whatever value, that's what the slope of your moment diagram is going to be. So in this first section here, we have a constant shear of negative 20. That means the slope of our moment diagram is just going to go down negative 20 kips per every foot, or negative 20 kip feet per every foot. And so we'll figure that out. Here is, on the triangles, is where it gets a little difficult. You don't have to be exact with your slopes. You just need to know when you're drawing it how the slopes work, which we'll get into when I'm actually drawing this. But the important part is that when the shear is 0, the slope of the moment is also going to be 0. So you either have a maximum or a minimum whenever the shear is 0. And that's why we always draw the line where it is equal to 0, because that's going to be an important part down here. So starting with our diagram, we're going to go ahead and start on the left part here. So at the left end, there's no moment acting on it at the end, so we could just say it's equal to 0, because there's nothing to cause a moment there. Here at A, this line here, we calculated this area to be negative 300. That means it's going to end up going down negative 300. And we can see this is a straight line. It means the slope is a constant negative slope. I'll go ahead and draw a straight line down there. Now the next thing we know is that area 2 right here was a positive 400 kip feet. And that means between A and this line here where it equals to 0, we're going to have a total change of 450 kip feet going upward. When we have that, it ends up going to 150 kip feet right here. And then I won't draw in the line for this section yet, but we know that from this 150 kip feet, A3 right here is going to end up being a negative 450 kip feet. And so when we get that 150 minus 450 is going to end up being negative 300 again. It's going to go back to where it came from. Now this is where a little knowledge about what the relationships are comes in handy. If we look at these relationships here, we say that we have a very positive shear here and a not so positive shear here. Well, that essentially means that the slope of this curve is going to start by going up at a high rate, at a very positive rate, and then as the shear starts going down in value, the slope of this is going to become less and less positive until it ends up being 0 right here at the dot. On the other side of this line here, we can see that we start with a not very negative value for shear. This not very negative value for shear means that we're going to start going down at a somewhat gradual rate. And as the shear starts getting more and more negative, the slope of this is also going to become more and more negative, and more straighter down, I guess. So we'll go ahead and draw this in, just approximating. We'll start very slow, steep, go to about 0 here, and then we'll start gradually and go down to there. Should be about a curve, maybe more like a parabola than what I drew here, but any curve like that should be fine. And so we can go ahead and look at our right end over here, and A4 ended up being a positive 300, and that works because it takes us all the way back up to 0, starting with our negative 300. So some quick advice about this is no matter what your diagrams look like, they should always go back to 0 on the left and the right ends, if that makes sense. So here, we end up going all the way through here, and it ends in this little section at a positive shear of 20. It ends up going back to 0 because we have a reaction force on the end pushing it down to 20. So same thing for this moment. There were no moments on the end of this beam, so it had to go to 0 by itself. And using our relationships here, the moment diagram ended up going back to 0 by itself, which is where it needs to be. If you're ever doing this and it doesn't equal 0 on the ends, you did something wrong. And so that's something where you'd want to go back and check your work. So that's kind of a nice way to watch your back, essentially, and make sure you're doing something right. Does anybody have any questions on the work that we did on this one? Okay, I'll go ahead and move on to the next one. I think these are fairly simple. So another quick thing is if you wanted to find where this is equal to 0 here, where that's equal to 0, you'd end up taking a little section of the beam. You'd take the section of the beam from the left end all the way to where this section was. So in the part here where this diagram here, we'd take a cut somewhere in there. And then doing that, you'd end up solving for the internal moment force based on everything that's happening to it. And I'm not going to quite go into the work here, but essentially you're going to find what the sum of the moments about the cut are. They're going to end up equaling to m plus a whole bunch of other numbers, right? So you're going to have the moment caused by this force and the distributed load. And that's all going to equal 0 because the beam is static. Well, when you do that, we're solving for this place here where the moment is going to be equal to 0. And so when you solve for this and you have the m plus all of this stuff, we know that m is equal to 0. And we're just going to end up getting an equation where we have a whole bunch of other numbers that should equal 0 eventually. And that's how you'll solve for x. Does anybody have any questions for that? I'll run through it on the next one, I think, a little more detailed because it asks for it. I'll go ahead and get another one out. This is another diagram one that we want to run through. This one's a little more complex than the other one. It's got some stuff. This is going to look a little more similar to your quiz, I would say. And so again, it says shear and bending moment diagrams for the beam shown, and label maxima, minima, and 0 locations. I'll go ahead and give you guys the reaction forces. So AY we have over here acting upward at 495 pounds. And then BY over here is acting upward at a 505 pounds. Okay, and I'll try to go through this one just a little bit quicker because hopefully you guys have gotten the gist. We're going to start with our shear diagram down here, so V, and our units should be in pounds instead of kips. I'll go ahead and draw straight lines where everything should change. So the shear should change here at A, where it goes up. Then this distributed load doesn't change anything at A until we get to B, where the distributed load ends and there's another force acting on it. So I'll go ahead and draw a straight line all the way down there. Here at in between this distributed load, there's a moment acting here. I'm going to go ahead and draw the line all the way down. It shouldn't really change anything in the shear diagram, but it will be helpful to see when we're calculating the moment diagram. So those are the lines. They're all 10 feet apart. We'll go ahead and get through this. So at A, we have a jump of 495, so we know that it goes up to 495 pounds right here. And then here we've got this 50 pound-foot distributed load acting downward. Again, the change from A to B is going to be this whole 50 pounds pound-feet multiplied by the 20 feet. And that's going to essentially be the resultant force, and that's going to be the total change. So 50 pound-feet times this 20 feet ends up being, should be a negative 1,000 here. So we're going to take our 495 and minus 1,000 is going to take us all the way down here to a negative 505. And as we can see here, the slope should be a constant negative 50 pound-feet going down. So we'll go ahead and draw a straight line there. And that's how our shear acts. The next thing we've got acting on it to cause shear is this reaction force here at B. It's 505 pounds going up. So that ends up working perfectly. It goes all the way back to 0 here. And from the end, from B to C, there are no other shear forces acting on it. So it's just a straight line all the way through the end. Okay? So that one's fairly straightforward with the shear. The moment is where it gets a little bit trickier. So the first thing we want to do is we want to find the areas under these, under the shear diagram, so we can calculate what our moment is. I'm going to end up splitting this off into 3 different areas. So we've got area 1 here. We're going to go ahead and split off this little triangle here where it meets off with this line at the change of moment here. We're going to go ahead and label that A2. And lastly, we're going to label this part here A3. So we need to calculate out what these 3 areas are. Well, the first one's fairly straightforward. We're going to have our 495. We need to solve for what this distance here is, x1. And again, we'll use what we learned about slope and rise over run. We're going to go ahead and take this 495 pounds divided by 50 pound-feet, and we're going to end up getting what should be a 9.9 feet. Another thing I like to do when I do these things is I like to check the units. Using dimensional analysis, we find out that the pounds are going to end up dividing out, and the feet's going to end up being our main unit. So we know that should be 9.9 feet. And that makes that the end here should be 0.1 feet. It's not to scale, but hopefully you guys can see that. So our area for A1 is going to end up being our 495 pounds multiplied by our 9.9 feet. And it's a triangle. We'll divide it by 2. We end up getting an area of 2450.25, and that should be pound feet. The next thing we're going to take a look at is our area 2. And so here our area 2. We don't really know what the height of this little triangle here is, so we're going to have to calculate that out. Well, one thing we know is that it's a change of 0.1 feet, and we know that for every foot that we go, we've got a 50 pound per foot change in load here. So this value here is going to end up being 0.1 feet times negative 50 pound feet, and it's going to end up being negative 5 pounds. So here at the top of this triangle, we've got negative 5 pounds. We can go ahead and use this negative 5 pounds here in our triangle. So it was negative 5. The base of this triangle was 0.1. We divide that by 2. It's a change of negative 0.25 pound feet. It's not terribly significant, but it's what we've got to work with. The next thing we've got is A3. So here at A3, we're actually going to split this off into 2 shapes and calculate the area of that. So A3, first we'll calculate this little triangle here at the bottom, which means we've got negative 5 is the height of this triangle, and the width of it is going to be 10 feet. And now we're going to add this rectangle up here. We're going to add the triangle, which the difference in this, or this height here, is going to be the negative 505 minus the negative 5, meaning we're going to have a height of negative 500 times a width of 10. We're going to go ahead and divide that by 2. We do that, we're going to go ahead and get an area of A3 is equal to negative 2550 pound feet. Okay, so we've got our 3 areas that we can use for our moment diagram. Any questions about that so far? Nope. Okay, we'll go ahead and go down. Pound feet. I'm not really watching the time here. It's 9:17. You guys get out at 9:40. Okay, I'll get done with this problem, and then we'll start your quiz. Okay, so we'll go ahead where this is equal to 0. We'll draw another line going down. And so we find A1. Our change in A1 is going to be 2450 and 25 or 0.25 pound feet. So we're going to go ahead and write that in 2450.25. And we can see that this is a triangle going down in slope. So the slope is very positive at first, goes to 0. So we're going to draw a curve going up like that. Next, we've got area 2, which is negative 0.25. It's just going to go down very slightly. That's a little exaggerated here, to 2450 even. The next thing we need to worry about is this change in moment here, this couple moment. When a moment is acting clockwise or going down like that, it means that there's going to be a jump in moment going down. So it's kind of counterintuitive because you always want to think that this way is going to be positive, but in this case, it's going to make our bending moment go downward. So it's 100 pound feet. We're going to end up going down to 2350 here. So from 2350, our last area is area 3 here, and it's negative 2550. We're going to end up going down 2350 minus 2550 is negative 200 pound feet. And this is going to be where the slope starts somewhat negative. It goes very negative. So we'll go ahead and draw that in. And then last things last, there's nothing here to change the moment until we get to the very end. So we'll draw a straight line here. And then this counterclockwise 200 pound feet is going to jump up to 0 there. So we end up getting what we wanted there. So we've got all of our information for this. Another thing that I forgot to say on the last diagram is you're going to want to label what order the graphs are acting in. And that's essentially the slope. You should know that a straight line, whether it's going down or up, is going to end up being first order. So whenever you have a straight line like this, you just always label it first order. The next thing you're going to want to know is that because of our relationships here, if this is a straight line here, this is going to end up curving. And since that is one, I suppose, curve past first order, this is going to end up being second order. This makes a little less sense when we're doing it like this than when we did with the formulas, because with the formulas you could actually see the polynomials and see what order they were by the exponents. This one is just where you have to know that wherever it was first order on the first diagram, it's going to go up to the next order on the second one. So if for whatever reason on the shear diagram we had a curve that was second order, wherever that curve was here, it would end up being third order on the moment diagram here. Now I don't really anticipate you guys seeing that in the exam, but I would definitely run through some problems and try to be comfortable with that just in case. The next thing that they probably want us to work through is they say label all maxima and minima, which is what we did. They also want 0 locations. And so for 0 locations, we'd have x2. We already labeled the 0 location for the shear. And so the 0 location for this would end up being a beam like that. And with the beam like that, it would essentially be this entire part of the beam up until some cut in here, because that's where it's going to equal 0. So we're going to have a 495 acting upward on it, and our distributed load acting constantly downward on it. And then somewhere toward the end here, we can draw in the 100 pound-feet. Then we'd label in our dimensions. And so this first part here, we've got 10 feet. The second part here, we've got x2. If you look at this diagram, this is going to be 10 feet from here to here in x2. So hopefully that makes sense in the scale of what we're doing here. And this is going to be negative 50 pound-feet. And then we're going to go ahead and draw the moment in here. I'm not going to draw the shear or the normal just because they don't really matter for the sake of this problem. We're going to go ahead and sum the moments about the cut. And so summing the moments about the cut, we're going to get m. And then this is going to get kind of messy and everything, but we're going to go ahead and write all the forces causing a moment. So we're going to have around here our 50 pound-feet distributed load multiplied by the total distance is going to be 10 plus x2. And then that's going to be half of the 10 plus x2 over 2. So that's the moment from that. Next, we're going to have a negative moment going from the 495 going at 10 plus x2 feet away from that. And then lastly, we're going to have the 100 pound-feet acting on it positively. And all of that is equal to 0. Well, we're solving for where moment is going to be equal to 0 here, so we can just set m is equal to 0. And then when you expand out this whole equation, you should get a regular polynomial with x squared or whatnot. You'll go ahead and solve that, and you'll get that x2 is equal to 9.78 feet. And that's how you'd go about solving that. I would get more detailed in it, but it's just algebra from this point here, solving for x2. This is really what matters, that you find that. But otherwise, that's all the information you really need to include on these diagrams. Always put your units in. Always label the zeros if you can. Sometimes it doesn't ask for it. So if it doesn't ask for labeling the 0 locations, like on something like this, you'd probably be fine getting away without labeling it. But definitely label your orders, your first order, your second order, and then all the numbers along this here. But anyway, without further ado, I'm going to go ahead and get your guys' quiz out.